Welcome back. In the previous lesson, we built the three diode models: silicon at 0.7 volts, germanium at 0.3 volts, and the ideal 0-volt model. Today, we put them to work. We will solve three classic textbook problems step by step. Same diode, same resistor, same source, but the answers change dramatically depending on which way the diode is pointing. By the end, you will know exactly how to find VD, VR, and IR for any single-loop diode circuit. Let us start with the simplest case, a silicon diode in forward bias. Here is the first circuit. A silicon diode in series with a 2.2 kΩ resistor driven by an 8-volt source. The diode is pointing in the same direction as the current would naturally flow, so this is forward bias. Three things we want to find: VD, the voltage across the diode, VR, the voltage across the resistor, and IR, the current through the loop. Step 1. Is the diode on? We have 8 volts pushing current forward, and the silicon turn-on voltage is only 0.7, so yes, the diode is on. When silicon is on, we replace it with a 0.7 volt drop. That is our first answer. VD equals 0.7 volts. Step 2. Apply Kirchhoff's voltage law around the loop. 8 volts equals VD plus VR. So VR equals 8 minus 0.7, which is 7.3 volts. Step 3. Ohm's law on the resistor. IR equals VR divided by R, which is 7.3 volts divided by 2.2 kiloohms. That gives us 3.32 milliamps. 3 answers, 3 lines of work. And here is the formula you will use over and over. I equals E minus 0.7 all divided by R. Now I'm going to flip the source. Same diode, same resistor, but the 8 volts is connected the other way around. The diode now sees a negative voltage at its anode. This is reverse bias. Will the diode conduct? No. Reverse biased silicon stays off. It acts like an open switch. Open switch means no current can flow. IR equals 0 amps. That is our first conclusion. If there is no current, what is VR? 0 volts. Ohm's law, V equals I times R, and I is 0, so VR is 0. Now apply KVL again. 8 volts equals VD plus VR, but VR is 0, so all 8 volts must drop across the diode. VD equals 8 volts. Notice the lesson here. Just by flipping the source, everything changed. The diode went from on to off. The resistor went from active to dead, and the diode went from a tiny 0.7 volt drop to swallowing the entire 8 volts. This is why polarity matters so much in real circuits. Now for something more interesting. 2 diodes in series, both forward biased. On the left, a silicon diode with 0.7 volts. On the right, a germanium diode with 0.3 volts. Powered by a 12-volt source through a 5.6 kiloohm resistor. Find V_O across the resistor and the current IR through the loop. The trick here is recognizing that since both diodes are on, we can simply replace each one with its forward voltage drop. And then it becomes plain old algebra. Apply KVL around the loop. 12 volts must equal the silicon drop plus the germanium drop plus VO. 12 equals 0.7 plus 0.3 plus VO. Combine the diode drops. 0.7 plus 0.3 is 1 volt. Solve for VO. 12 minus 1 equals 11 volts. VO equals 11 volts. That is our first answer. Now for the current. Ohm's law on the resistor. IR equals VO divided by R, which is 11 volts over 5.6 kiloohms. That gives us 1.96 milliamps. Notice something elegant here. When you have multiple diodes in series, all forward biased, you just add up their voltage drops and treat the whole stack as a single combined drop. 2 diodes? Add them. 3 diodes? Add all 3. The principle is the same. 4 LEDs in series at 2 volts each? That is 8 volts you need to overcome before any current flows. Same algebra. Let us recap the workflow for any single loop diode problem. First, look at each diode and decide forward bias or reverse bias. Forward bias silicon means a 0.7 volt drop. Forward bias germanium means a 0.3 volt drop. Reverse biased means no current at all. Second, apply Kirchhoff's voltage law around the loop. Source voltage equals the sum of all the drops. Third, use Ohm's law on the resistor to find the current. 3 steps. Always the same 3 steps. Now you have a procedure that works on every single loop diode problem you will see. In the next lesson, we put this to use on rectifier circuits, where the diode flips between on and off many times per second to convert AC into DC. See you there.